In this video, we will review how to analyze your competitive ELISA data. You will need your data generated from a plate reader and software capable of fitting 4PL data. We will begin with the MyAssays online tool, then Prism software, then finally Softmax software. Feel free to skip ahead to the instructions for the software you intend to use. The standard curve data is preloaded into MyAssays for each Arbor Assays kit. To gain access to this, you can follow the link in the kit insert or visit www.myassays.com and search for your ELISA of interest. Once there, you can paste in your plate details from the plate reader, define your samples and dilutions, and proceed with the calculations. For further support with MyAssays analysis or subscriptions, please visit myassays.com/support.aspx. For data analysis in Prism, from the opening dialog box, select an XY data table and the number of replicates for your Y values. In this example, the data has 2 replicates. Enter the NSB values in the top row. Enter the concentrations of your known standards in the X column. Include a 0 standard that represents your B0. Enter the signal output for each standard and unknown in the Y columns. To subtract the NSB values from your dataset, click Analyze and choose Remove Baseline and Column Math. Change the definition of baseline to Selected Rows and click the first row. Remove the checkmark for Create a new graph of the results, then click OK. We now have the average net OD for each standard and unknown. To generate a standard curve and read the unknowns off it, click Analyze and choose Nonlinear Regression Curve Fit. Select Sigmoidal 4PL, X is concentration. Make sure to check the box to interpolate unknowns from the standard curve. In this case, we are using a 95% confidence interval. This will generate a graph of your standard curve and can be edited to display the x-axis in a log scale. The Results section under the Interpolated X Values tab displays the calculated values of your unknown based off the standard curve. To calculate percent binding and generate a percent binding graph, return to the Baseline Corrected Results section and click Analyze, and choose Transform. Select User-Defined Y Functions from the Function List menu and select Add. We are going to call this function %B over B0. And the formula will be Y equals Y times 100 over B0. Enter the net OD of the B0 value, which is 0.854 in this case. Hitting OK will calculate binding values for your standard and unknown values, as well as display them in a graph. If you prefer to calculate your unknowns using binding values, you can perform the nonlinear regression analysis described previously. Be sure to save your analysis before closing Prism. For data analysis in Softmax, from the opening dialog box, copy your plate reader output. Highlight the entire plate template in Softmax, then paste. Update the plate map to match your experiment. Here we are using samples run in duplicate. Be aware that plate layout, concentrations, and other parameters will vary based on each individual kit. Select Template and highlight the wells that were used for the NSB. Click the drop-down and select New and name the group NSB. Repeat this process for your B0 wells. Highlight the wells used for standards. Multiple columns can be selected at once by holding the Shift button while selecting. Click the drop-down, select New, and name your standards. Change the column format to standards and change the units to reflect that of the kit. In this case, picograms per milliliter. Highlight the first column of standards and select Series in the upper right. Change the starting value to reflect the concentration of standard 1. Edit the Step By value to accurately reflect the dilution factor of the standards. Change the Start From to Left if duplicates were run vertically. Change replicates to 2. Repeat this process for any remaining standard columns. Change the standard number to the next standard sequence from the previous column. Select Series and repeat the previous process. The starting value does not need to be changed. Highlight the wells used for samples. Click the drop-down, select New, and name your samples. Change the column format to Unknown Dilution, and change the units to reflect that of the kit. Highlight your samples and select Series. If all samples are diluted the same amount, change the starting factor to reflect your dilution factor. Change the Start From to Left if duplicates were run vertically. Change replicates to 2. If your samples are all diluted uniquely, highlight the wells while in the Series tab and use the dilution factor box to indicate the dilution factor used for each sample. Now we need to code the wells for the analysis. Start with the NSB and delete all columns except the sample and wells columns by highlighting the ones to delete, then pressing the Delete key. Click Column Formula Editor to add a new column. First, add optical density to report the signal from the plate reader. Name this column OD in the name field. Insert the equation shown to pull the values from the plate into the NSB field. Add another column to average the OD values from the replicates. Name this column Mean OD and use the equation shown to average the replicates. Add a third column to calculate the standard deviation. Name it SD and use the formula shown to calculate the standard deviation between the replicates. Add another column to calculate your coefficient of variance, CV. Name the column CV and use the equation shown to calculate it. Click the Summary Editor to communicate values between other data fields. Name the description Average NSB. Select Hide Name and use the same formula as Mean OD from earlier. Move on to the B0 field. Delete the columns as shown previously for the NSB. Highlight the OD, Mean OD, SD, and CV columns from the NSB. Copy and paste them into the B0 field. The columns will automatically populate with the correct values. Add an additional field named Net OD to subtract the NSB from the B0 values. Use the equation shown on the screen. Use the Summary Editor to calculate the average B0. Name the description Average B0. Select Hide Name and use the equation on the screen to calculate this average. Add another data field named %B over B0 to calculate the maximum binding. Enter the formula shown. In the Standards field, confirm that the range of standards is consistent with the kit insert. Delete default fields, keeping only the sample and concentration columns. Copy and paste all new fields from the B0 field. Add a new column named backCalculate to assign concentration values to the standard points using the 4-parameter curve formula based on the binding values. Use the equation shown on screen. It will show an error until we make the accompanying graph. For now, select Ignore Error. To make the graph, select Experiment, then New Graph. Select Standards as the source. Select concentration for the x-axis and %B over B0 for the y-axis. Name the series Standards. Then, click OK. All our competitive ELISA assays use a 4-parameter best fit curve. Select 4-parameter from the Fit drop-down menu. Double-click graph number 1 and name it %B over B0 graph. After naming, the back-calculated values will appear. In the Samples field, delete the default columns, saving Sample and Wells columns. Copy and paste the new columns from the Standards field. Rename the back calculation column to Average Concentration. This column will calculate average concentration for each sample based on the binding curve. Add a column for the dilution factor using the formula shown. Add a final column to determine the concentration of the original sample before dilution, called Adjusted Concentration. Use the formula shown on screen. Finally, we will create a standard curve using net OD values. To make the graph, select Experiment, then New Graph. Select Standards as the source. Select Concentration for the x-axis and net OD for the y-axis. Select 4-parameter from the Fit drop-down menu. Then name the graph Standard Curve. Be sure to save your analysis before exiting.